To the Institute for Astronomy here on Maui. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And I put together these talks with fantastic speakers like Dr. Jefferies. I'll give you a little introduction, and everyone knows the tradition is I have to screw up at least once in the introduction, right? Okay, good. Good. Let's keep a count this time. So Stuart is a scientist here at the Institute for Astronomy. He came here. No, that one was right. Okay, he's been to South Pole. He says 6 or 7 times. He wasn't quite sure. He got his PhD at Imperial College, and he was working in Arizona for Bartol. Yes. Bartol Research, which is actually not in Arizona. He said he made it out there about twice in the years that he worked for them. Worked for the National Solar Observatory for about 12 years. Came to Maui about 14 years ago. And he's an expert in helioseismology, also image blind deconvolution, which is you watch CSI and they enhance the image. That's one of the things he's brilliant at. And at this point, I will turn the time over to Dr. Jeffries, and let's give him a big Maui welcome.
Okay, good evening. Thank you. Why? How? If you've had children, you know that these simple questions are probably the most hard questions to answer sometimes. Okay, so we're at the airport. Going to the airport with your child, look up. Mom, Dad, why do we have to put our bags in that machine there? I think I got this one. Well, that's because they need to check that nobody's trying to take anything onto the plane they shouldn't be taking. Why? Why don't they just look in the bags? Okay, I got this one as well. Well, if they took the time to look in every single person's bag, we would never get on the plane because there's too many people, so they put it in the machine. Okay. Then comes the one that you know's coming. How? How does it look in the bag? It's like, okay, now I have a choice. I go deep or I stay shallow. I think I'll stay shallow. Well, when they put it in the machine, they have waves. They're called X-rays. And those waves can actually look into the bags, and they make pictures that can be seen by the computers, and then the computers make a picture that they can see, and they can see into the bag. Oh, feeling quite proud of myself now. Going on. Why are they standing like this in that thing over there? You say, well, they're doing the same thing. They're looking in under the jackets and everything, see if people are carrying things they shouldn't do. And again, they're using waves. They're using waves to look inside. Ah, okay. So another example of when we use waves to look in something. Okay, we're not feeling too good. We're having a bit of a rough time, if something's wrong, go to the doctor, we do the 500 blood tests, don't know what's wrong still, and then they say, you need to go and get a CAT scan. You need an MRI. So we go in, we sit in the machine where we can barely think because it's making all the noises. We come out, and they have pictures. They have 3D pictures of our insides, and hopefully they can find out what's wrong with us. But again, we've used waves to see what's going on inside. With the MRI, we use radio waves, and we have magnetic fields. And then in the CAT scan, it's X-rays again. Okay, so with that kind of flavor, this is what I'm going to be talking about tonight, is using waves to look into things, except for I'm going to be talking about using waves to look into the 4 biggest things in our solar system. Okay, so time for the questions. Why? Okay, well, if we look into the middle of these objects in our solar system, we're going to be able to figure out how they evolved, how they formed, why they're there, things we don't know very well. Okay. So how are you going to do it? Well, I'm going to use waves, I just told you. But I'm going to use sound waves, and I'm going to use gravity waves. And these are waves that are being produced by these bodies on their own. But I'm going to use them. And I'm going to steal all the techniques we use from seismology here on the Earth. Okay, with that said, we'll have a quick journey through the 4 objects I'm going to look at. So the first one I'm going to might as well start with the biggest. And the biggest object in our solar system is? The sun, obviously. Okay, sun, wonderful object. Most important thing to us in our lives. It gives us heat, gives us warmth. Without it, we wouldn't be here. Okay, it's 93 million miles away from us. It's huge. We can get about 1 million Earths inside the sun. Okay, it's let's see, it's very hot. It's 6,000 degrees on its surface, and if you go down into the very core, it's about 15 million degrees or something, where the nuclear fusion's taking place. But it has this very peculiar property too. As I move away from the surface, it gets hotter again. A little bit strange, right? It's like being by a fire. It's a bit too toasty here. Oh, no, that's even toastier. Okay? We don't know. It's an enigma, 50, 60-year enigma. We don't know what really caused it. We have a lot of theories, but we don't know. Okay. So the sun is made up mainly of hydrogen. As Pumbaa would say in The Lion King, it's a big ball of hot gas, right? It's mainly hydrogen and helium. Now, if we look at the sun with our eye like this, first it's going to hurt if we look with our eye. So let's, okay, imagine I have something I can look at it with. It looks pretty unimpressive, but it's far from that. The sun is spectacular. Okay, the sun is constantly it's dynamic. It has a lot of oh, there we go. Thank you. I can look at the sun now. So the sun is magnetically very active. Okay, and then the way, how do we, and one of the signatures of this magnetic activity is we have spots on the sun. They're called sunspots. Now, they were first seen and recorded around about 2,000 years ago by the Chinese. They must have seen them through clouds or something like this. But beginning in the 1600s, with the advent of the telescope, then we started mapping these sunspots. Now, in this video that you're seeing up here, the active region of these sunspots are actually where the bright patches are here. Now, one of the things about the sun is when you have these active regions, that they can cause the sun to eject lots of its material out into space. This is ionized plasma that's being ejected out into space. Now, if you think about this, I can get 100 Earths across the diameter of the sun, so you can see that the Earth would be something like this here. All right. So, now one of the things about the ejection of these plasmas, and here you can see something called coronal mass ejections. And so the size of the sun here is roughly where this circle is, and same again here, and you'll see just how much mass, it's billions of tons that's being spewed out. Now this is of concern to us, right, for several reasons. Anybody have any ideas why?
Cell phones.
Cell phones, exactly.
Yeah.
When it comes towards Earth, okay, into our magnetic field and everything, it can affect our communications, and GPS especially, which is very important for our defense. We certainly don't want those going down. It actually generates electricity in the telephone, in the wires that go across, the electrical wires that go across, and the also the pipelines and things like this. And so it can be very destructive. So what we would like to do is we want some sort of predictive capability. It would be really nice if we could know, when one of these things was going to happen. Okay. Now, the solar activity comes in cycles, as probably most of you know. It comes in cycles at roughly 10, 11, 12 years, something like this. And then since we've been recording with telescopes since the early 1600s, you can see this periodic behavior. And so what happens is the number of solar active events like this, like solar flares or coronal mass ejections, tends to be larger near the most active periods. Okay? So one of our targets with looking at the sun is if we can look inside the sun and we can figure out what's going underneath, maybe we can start developing some sort of predictive capability. Maybe we can figure out when these events are going to happen. This is one of the main targets. Okay. Well, I gave the game away. I was supposed to ask what's the next biggest one, but obviously it's Jupiter. Okay. Now Jupiter's still not bigger than the Earth, right? It's about 11 times, you can get about 11 Earths across, for about 1,300 of them in the volume here. Jupiter's temperature at the surface, I think, is about -100, a little bit different from the Sun. Okay, again, it's a big ball of gas. It's mainly hydrogen and helium. What we believe is going on in Jupiter is that right at the center of it, there's a rocky core. And then as you go deeper into it, because the pressure's increasing, that some of those gases, the hydrogen and helium, are actually turning to metallic hydrogen and helium. So that's what we believe is going on there. What's the next largest one? Saturn, obviously. Okay, Saturn. Now Saturn is also the same as Jupiter, and it's called a gas giant, and it's again because it's mainly hydrogen and helium. Its internal structure's essentially the same. Its temperature's a little bit on the surface, a little bit cooler. I think it's about -140 or something like that. But again, what we're interested in is, can we see inside? Can we see where the hydrogen is turned into metallic hydrogen? Can we see where the core, where this rocky core starts? We don't know. We only have models, and there are many models that fit what we can tell on the outside. And the last one? Yes, thank you. Okay. One thing about Saturn that is just for me, when I was looking up about Saturn, I didn't know, but I'm sure all of you did, was this amazing thing on its north pole. It has this hexagonal field, right, with all these turbulent winds going around. In fact, going back here to Jupiter, this is one of the things too. With Jupiter, the belts you have in the atmosphere, you have all these belts of wind that are just going in different directions. And in places where the two belts counter directions, you can get storms like this one. This is the Great Red Spot, which is essentially a typhoon that's been going on since the 17th century. Okay, so we come to our last one, and it's your. And so these are the targets. These are the targets of our research here. So tonight I'm going to tell you a little bit about how we're starting to look at all of these different objects. Okay, now because all of these objects are mainly gas, then they have they can support convection in their outer layers. So what I'm showing you a picture here is of the sun. This is actually taken with the Swedish telescope, and this shows a phenomenon called granulation. So this is actually just basically showing us convection. So convection is just, hot air coming up, and then hot gas rising up, and then cooling and falling down. We've made some significant advances in the last, 2 decades or something, about modeling this, about what's happening in these convection zones. And so we're at the stage now where if you just imagine just a small piece of this, okay, and we can model a small box. We don't have the compute capability to do large things. It's hard enough to do something small. But you can see that we can get pretty close to what might be going on in the sun. So this is great, because if we have a model, right, I'm looking at the top, I can just flip it up, and I can look however I want. And so if we do that, then we see this. And what we see here is that the black is showing cool gas. So what we have is hot plasma coming up, and then it cools very, very quickly. And as it cools, it falls. And it falls very, very fast. In fact, it falls at a speed which exceeds the local sound speed. So if something exceeds the local sound speed, something happens. Yeah, so we get shock waves and we get sound waves launched, just like a plane going through the barrier. So what you can see is in these dark regions here where the gas is falling down, we're getting all these excitations, all these shock waves and sending sound waves, and these are going around the sun all the time. So we have sources of sound that are everywhere, random in space, random in time, everywhere on the sun. And we think also on these... No, what we can do, I'll come to in a minute. So please remind me in just a sec, all right?
How is the scale of the what makes the scale of the granulation?
What makes the scale of the granulation?
Size of it.
That's a good question. I don't actually know what actually causes it. I mean, they are about the size of Iowa, basically, all right? But what actually gives it a distinct scale is supposed to be in a cascade of scales, like Kolmogorov or something, is what you mean, right? Yeah. Well, there you go. Exactly. But okay, so what we have is we have the launching of the sound wave. So what happens then? So we have a sound wave, and the sound wave is launched at the top near the solar surface, and it comes down, and it's at some angle. So remember, I've got 15 million degrees here, 6,000 degrees up here. Well, except for the sunspots, they're a bit cooler. They're 4,000, but we'll come back to that later, maybe, if I remember. So we come here. So as the wave comes down like this, it's hotter here than it is here, so it travels a little faster. So what happens is the sound wave comes down, refracts around, comes back up to the top of the sun. When it comes to the top, there's a steep change in density. That's like hitting the wall. So it reflects off there and goes down. And so these sound waves get launched, and they go around the sun, bouncing around, and they lose a little bit of energy at each bounce, but if they make it all the way around the sun, they can constructively interfere. Okay, and they make a constructive interference. The different angles that the waves get launched at travel to different depths. So one that's launched like this travels down to, I don't know, 2/3 of the way down. And another one that gets launched up here at a shallow angle only skips around the surface. And so you can see that these waves, as they go around, they're sampling what's happening inside the star or the planet as you go along this path. Yeah?
It's surprising that they don't get
They do get damped out, but their damping times are of order days or longer. So they stay coherent long enough to make it around the sun. Oh. Repeat the questions. Oh, I'm sorry. I'm a novice. Excuse me. All right. Now, so what does it look like? So they've got the sound waves coming around, come to the surface. What happens at the surface? Well, at the surface, okay, it pushes out like this on the surface. The surface moves up. The whole atmosphere moves up and down, okay? And then what happens is each sound wave ends up in some sort of pattern on the surface with this interference. Now, this is really exaggerated for the size of of what's happening in the movement, but it shows you some sort of complicated pattern that goes on. And there are about 10 million different oscillations. So if you take 10 million different patterns like this, and you superimpose them on top of each other, you get something like this. And this is actually a picture of the sun taken Christmas Day, 2003, from South Pole. Not that it makes any difference, but it shows the superposition of 10 million, roughly, of these modes of oscillation. Now, something that I want to go back to with this, let's think about one of the things, if we want to look into the center of the sun, is we want to look at ones that come straight across, right? These are the important ones. What do they look like? They look much simpler than this. The one that goes straight across, okay, is like a breathing mode. So if you take a balloon, and then it goes down, up, down. It's like this. Yep, just radial expansion and contraction. The next one is like, kind of like a heartbeat. You've got two pieces like this, and it goes in, and so on. Now, these are the ones that come straight through, and slight curvature like that. These are the most important ones. But there's one other thing that I think you can see if you look carefully here. It's important. Because the sound speed's increasing this way, they spend most of their time up here. Slow, fast, slow. So the properties that they measure, they get some of this information, but they don't spend much time there. Okay?
But in these oscillations we see, what is the typical amplitude of the surface deformation?
Okay. Tens of, yes, for individual one. Oh, sorry. What are the amplitudes of these oscillations when they're at the surface? So typically, for an inter one, you've got tens of centimeters or something like this. But when you add up lots of them, you get meters per second. Okay, tens of meters per second. But the individual ones are of order 10 centimeters. In fact, there's a type of wave called the internal gravity wave, which is not the one I'm talking about tonight, which is trapped in the deep interior, which comes out. This has something of millimeters per second. So we're trying to measure from 93 million miles away that. Yeah. Right? So, and it's like anything else. What happens is the longer I observe for, the smaller the amplitude of the waves I can see. Okay. Right, now, there's another type of wave. I should stand here, I shouldn't put... The next one is what we call an internal gravity wave. So think about this. Imagine that I've got the atmosphere above me here. I don't have to imagine, it's there. I've got the atmosphere above me, okay? And then the atmosphere the density gets less as I go up, right? So this is what's called a stratified medium. So if I was to take a parcel of gas there, and I was to move it somewhere, up, down, which way should we go? Let's go down, okay? I've moved from a less dense place to a more dense place. So what happens to what does that parcel of gas want to do? It wants to go up. Okay, it goes back up. Now it goes, but it doesn't stop where it started. It goes past. Now it's more dense than everything around it. So what does it do? Yeah, it comes down. So this is an oscillation, and I guarantee that everybody in this room has seen gravity waves. We see them all the time here in Hawaii, nearly every day. Any clues? As soon as I show you, you'll... Yes. There they are. This is what we see. When you look up, especially here on Haleakala, that's what you're looking at. And Haleakala is acting as the source because it's a mountain, and so you've got the wind coming, and then you disturb the medium, and you get the gravity waves. We see these all the time here. Now, what's interesting about gravity waves is that they can travel very long horizontal distances. They can carry a lot of mass and energy with them. Our weather forecasting capabilities have improved many fold since we figured out that they affect our weather. Okay, they're very influential. I just grabbed this. I stole this off the web. I like this. This is Iowa again, my favorite place tonight. Here's a gravity wave, time lapse of a gravity wave there. Their periods are long. You would not notice this. You know, we can't. Our attention span now is society as much. Yeah. This is ours. This one here. Well, you can see this is actually a bit faster, but they're of order. You know, quarter of an hour longer. Things like this. It's very hard to see it unless you've got time lapse. Now, this one I'm sure everybody's seen because I've seen spectacular examples of this when I've flown back from California. I think if you look at the plane when you're flying back from LA and that, you'll see this all the time. It goes for 2 hours at a time. I've seen it when I'm doing it. Anyway, so we've all seen these. Here's a picture of Earth from a satellite showing a really nice set of gravity waves. Any idea where this one's from? You know it's not Earth. It's Jupiter. This was taken by New Horizons as it went over Jupiter. There are gravity waves on Jupiter. Gravity waves have been seen on Venus. Gravity waves have been seen on Mars. Okay? They're everywhere, and they have a big influence. What about gravity waves on the Sun? Are there any there? I don't know. So yes, I'm glad I asked myself. All right, so let's think about this. So we've been talking about waves. Now, how am I going to observe them? Okay? So the way I'm going to observe them is I'm going to say, remember, the wave comes up, hits this piece, the part of the sun that's essentially rigid to the wave. The whole atmosphere moves like this. Now, in the sun's atmosphere, different elements absorb light that's coming from the sun, and so we get these spectral lines. They go dark in that place. So, if this was a spectral line in the sun due to some element, I'm going to say sodium, could be potassium, could be anything I want. Then, as the atmosphere of the sun moves backwards and forwards like this, what I'm going to get is this line is going to shift in wavelength. It's going to go red shifted for moving away, blue shifted towards me. So if I can make an instrument that looks at two specific wavelengths like this, and I look at the difference in the intensity between them, so this is brighter here, darker here. So if I was to take the difference between that measurement and that measurement, it would be 0. So it's not moving. However, if I've got some oscillations going on the sun, I've got two things going on. I've got backwards and forwards like this, but also if this line is not symmetric, if it goes up and down, just changes intensity, then that also causes a signal. But I can measure both of them, and it turns out that the velocity is just the difference of these two divided by the sum, and that takes out the intensity variation. So this is how I'm going to measure. I'm going to build an instrument. It's going to look at these very narrow passes, these narrow bands of light either side of some line on the sun, and it's going to tell me, and I can measure intensity or velocity, or both. Now, let's think about what the waves are doing. So I just told you that the atmosphere is moving, but also there's a little compression going on. So as there's the compression, things are getting hotter, colder, hotter, colder. So there's also little brightness variations. And those brightness variations are about a part in 10 in a million. They're small. Okay, so those are our two ways that we're going to look at these things. All right, so not going to dwell on this too much, but here's an example of an instrument we would use to look at the sun. Tonight when we finished, if anybody's interested at all, I have one that's open like this that I go over and we can discuss details and I can talk to you about it. But basically the product of it, basically the light comes in, goes through this. These are these two filters. All I'm going to say now is they're atomic filters. I use atomic gas to actually do the filtering. And at the end we separate into two cameras. So what does that mean? It means I get an image of the sun in a red wavelength and an image of the sun in the blue wavelength. If I difference them, I get a velocity signal. And here we see the velocity signal of the sun. If I change the polarization of the light on the input, and we won't go into it now, I can actually get a Doppler signal that's in a left circularly polarized light, which is different from one in the right circularly polarized light, because the line on the sun is different in those two. And if I take the difference between the two Dopplerograms, I actually get a map of the magnetic field. So I get magnetic field, Doppler velocity, and intensity all in one shot. So what I do is I measure this every 5 seconds, and I do it for months. Okay? Now, just a quick example here is these are some of the setups we have. So we have our instruments up at Mies Solar Observatory. We'll talk about that later. We take these to South Pole, and the reason to go to South Pole is very clear. During the austral summer, the sun just goes round and round and round, and we don't have any gaps in our data. Typically at South Pole, we can expect to get about 19 days with no break. So this is way cheaper than going to space, right? Way cheaper. The worst we've had is 3 days, but the most we've had is 55 days unbroken. It's truly spectacular, especially when you think about rockets. When you send rockets up and you grab a few minutes or whatever. So it's pretty good. The other thing that we started working on, which is what I wanted to bring up tonight, so you get a feel of what we're doing here on Maui, is that we're also looking to put these in space. And we figured out how to take this thing, which is like this, and make it into something like this. So we're actually working on some space projects, which I'll come to in a minute. And the other thing is we use the same instrument for doing both the sun and the planets. And here's an example of us. We're on the 2.3 meter at University of Arizona back in January this year, made measurements of Jupiter. We're there next week making measurements of Saturn. Okay, so how do we get the stuff out of the data? So we've got these pictures, right? We've got these pictures that just look like salt and pepper everywhere. How am I ever going to get anything out of it? Remember that salt and pepper is actually a lot of different patterns like this, just superimposed. So if I just take a mathematical mask of this, put it in the right coordinate system, multiply it onto my salt and pepper, then if there's anything in there, it'll give me a big number. If there's not, it'll give me a small number. And if I do that for every one of these patterns, and I end up with a whole set of numbers, and then I do that for every image I took in my whole data set, I can actually make a spectrum. I can see if there are any waves on the sun. So if I do that, and I stack them up, and this is a two-dimensional thing, I see this beautiful diagram with just thousands of modes of oscillation of the sun. Yeah, well, the first time back in the 70s, yeah, people didn't really understand what we were seeing. But what we have here, look, is I've taken different places. So, here's the different damping. The lines are fatter, where the waves don't last so long, and where they last a long time, they're nice and thin, right? So there's your damping. But the point is, what we have to do now is we just go in and we just say, where is that in frequency? This is just the frequency of the wave. I identify those frequencies. So I go through and I measure all those frequencies. Now I have a set of frequencies, okay? And it's with those frequencies that I can actually start finding stuff out about the sun. So the first thing I can do is I can take a model of the sun. And I can look from that model and I can say, what frequencies do I have? I can compare them to mine, and I can see how well my model does. Or I can do an inversion against it. This is kind of state of the art for where we are. So if you look at this, the discrepancies are less than 1% here. So you might say, okay, done. Don't need to do anything else. This is sound speed. This is the sound speed as we go into the sun from the surface. So you could think of it as density as well if you want. Okay, so this is the sound speed anomalies. But you can see right around here, just around about 0.7 or something, there's something off in our models. And as we go down to the bottom, you'll see the errors get larger. Well, remember, that's because the waves don't spend any time. They zip through, and there's not many of them down there. But it's a nice result, and we move on. Probably one of the biggest results that we've got was that when this all started, and we figured out what was going on, is we measured the differential rotation of the sun and how far it goes inside. Now, the sun, if you know or not, the equator rotates faster than the poles. At the equator, it's something like, I want to say, 25 days or something like this to go around, and it's like 33 days at the pole. So it differentially rotates. Different latitudes go at different speeds. What we found from using this technique is that it stays that way all the way in, then very close to 0.7, suddenly goes down. It's called a tachocline. It's a fancy word for it. It's just like a shear layer. Now, this is pretty exciting because the shear layer is where people think the magnetic fields on the sun may be formed, okay? And this may be the root of solar activity. So we want to study this area really well, but it's difficult because the waves are not spending time there. You'll notice that we don't go very far down. That's because the errors get big fast, all right? It's because we're not seeing the waves, enough of the waves we want to, and that's an important point. I'm going to come back in a second to that. Okay, so we use exactly the same thing for the planets as we're going to use for the sun. Basically, we're going to look at these sound waves, and we're particularly interested in the ones that come across from the back, okay? Now, for Jupiter, so we're going to do this for all the planets. For Jupiter, you might say, whoa, hang on, slow down, buddy. Okay, NASA have just put a satellite up that's going to arrive at Jupiter in 2016, Juno I think it's called, and it's going to measure the gravitational field of Jupiter. And then from that gravitational field, I'll be able to look at the harmonics, and I'll be able to figure out what the internal structure is. And I say, you're right. You're absolutely right. But you know what? You're not going to find it out very well because the harmonics that are going to be measured only see into about the top 10% of the sun, okay? Imagine that we see these waves, these oscillations, sound wave oscillations on the sun, and we see a spectrum like we do on the sun. Then we can cherry pick a set of oscillations, and we can make a kernel, a way of looking at a part of the sun that's very sensitive. We'll be able to see, well, is this where we get helium droplets? Or we can go down there. What does the core look like? So we can actually look inside, we'll be able to look inside the sun and identify all these different regions where things might be going on. Okay, to give you some, I think this is depth in the sun. This is the top, Jupiter. This is the top, this is the bottom. This is where Juno's going to tell us about it, and this is where sound waves are going to tell us. If we can do it, it's no contest. Now, you say, well, can you do it, or are you just blowing smoke here? I say, there's actually evidence, ground-based evidence. This came out a few years ago from a group in France. They took a series of 7 days, and even though it's not concrete proof, all the dotted lines are where waves are expected, modes of oscillation are expected to be, and the correlation's very high. So,
Compared to their model?
yes, as compared to a model. Now the thing is, we're trying to use it to find which model's right, so you have to be a bit careful there, right? Yeah, but they couldn't get, this is just like a tease. This is how the seismology of the sun was 50 years ago. It's teasing us. So we're chasing this now, but with a completely different instrument. And this is what we're after. This is our target, basically. What we want to do is that JPL has shown a lot of interest in this, and they're pushing hard now to do a Uranus Explorer mission. Okay? And the idea is we're going to take one of these, a very small version of our instrument. We're going to put it on a launch vehicle, and we're going to send it off. Departs in 2022. It does a flyby of Jupiter in 2023 to get the gravitational assist. But we can also do seismology at Jupiter while we're there on the way by. Thank you very much. And then, of course, we get to Uranus at 2030 when I have to ask my daughter or her husband what the results were. Let's see. And so what we've done, so at the moment, what are we doing? We're actually pursuing a more rigorous proof of concept so that we can get some leverage with things. So I said we've done some observations on the 2.2. We've got a 7-day data set with, and this was taken in January, of Jupiter. And we're analyzing the data now. I was hoping to have something for tonight, but that wasn't the case. All right, so that was global. Yes, Joe?
What would be the best gases to look at? What atomic filters do you want to use for?
Okay, the question was, what would be the best gases to look at in the atomic filters? We're going to use, so what we're doing is we're going to be looking at reflected sunlight off these. So probably our best one is going to be potassium, because the line is not as deep as it is for sodium, so there's a few more photons there. But it's still very narrow, so we get good sensitivity. Okay, so what we've talked about so far is just basically this global seismology, okay, that the waves go around and they interfere with themselves and they set up these standing wave patterns. But there's another trick in our bag of tricks. It's called local seismology, and this is directly analogous to what we do on the Earth. You know, where you put some dynamite in the ground and you put your microphones everywhere, set it off, and you say, yep, I'm going to be getting my oil right here. Well, it's the same on the sun. If you identify a source here, then waves will travel different distances, and if you just put your microphones at these different distances, you can measure this travel time along here, and from there you can infer what's going on underneath. So this is just basically showing that there's a continuum of these waves of different distances and times. But what it enables us to do is we can go to something like a sunspot, and we can actually construct it so that we can see what the 3D structure is under a sunspot. I haven't been able to do this before. And so not only that, but from that, if you do this many times over a period of time, you can see what the activity is, what the dynamics are. And so this is what's happening under a sunspot that was studied a few years ago by Kosovachev and some people at Stanford. And they call this the teapot model, because you can see all the circulation and everything going on. But what it's doing, it's giving us a first glimpse into something that we've never been able to see before. Okay. Here's another cool thing that we can do. We're looking at this side here, but on the back side of the sun, there's a sunspot. It's lurking there. Okay? And we know that if it comes around and it's a big one and there's some activity, it could launch a coronal mass ejection or a solar flare or something, and the amount of time we have to respond to it goes down dramatically. So we want to know what's happening on the back side. So we can, by doing a careful analysis on the front, we can pick the waves we want to see, and we can arrange it so that we pick ones that form a focus at any point. And we can just move that focus around. How well does that work? Well, what we have here on the bottom is that we take pictures of the sun so we can see the magnetic activity. So this darker blue one, that's the real magnetic activity. This is time. And this is what we infer by looking at the back side. So there's where the spots are. When they're on the front, they rotate to the back, and we pick them up on the back. We're actually able to image the far side of the sun. We can monitor things. Now, this is really great. This gives us some advanced capability for warning for our satellites and things, so we can put them in safe mode. But it's not really good enough. It's actually, its success rate is not bad, but we want more. We always want more. So remember, what we're after is we want to see rays that come across here and there. How are we going to do it? Well, we're going to put a satellite. If we took another satellite and put it around the sun, that would do it, right? Just imagine here. So the two areas I'm really interested in on the sun. One, this place here where the differential rotation was like a shear, because that's where the solar magnetic field may be generated. And the core. We have no idea what's going on. How did the sun form? Did it spin down? Did it? Who knows? So we want to see that net. So you can see here that I can form a focus here as I move around. And of course, as I come to the back side, I can probe very close to the core. It's not possible for me to do it from here, remember, because if I see it there, it has to bounce at least twice before I see it again. So this is a strategy. So we're putting together with JPL again a mission. It's called Safari. We got this close to getting funded last year. We were deemed a flyable mission, which is a huge success, but there wasn't any money. I haven't heard that before. But we're hoping to get money this time, and JPL is sinking a bunch of money in. So the idea here is that IFA, we're involved in two aspects of this. We're helping design the instrument to go on board that'll fly around the back, but we're also going to be responsible, if we get the money, to put 6 stations around on Earth as our other site. And they're going to go in some sites that are already used for solar seismology. It's in Australia, Udaipur in India, Sutherland, South Africa, Canary Islands, Cerro Tololo in Chile, Big Bear, and of course Hawaii. Okay, so we're going to build them and set them up. Instrument, how big is it? Well, it's about this here. This was what you saw before with the quarter. It's about this big, and that whole thing is about maybe this big. So we've spent a lot of time on shrinking things.
How far will it be orbiting from the sun?
Oh, gets to 0.2 AAU, I think it is. Pretty close. Yeah. Yeah. Oh, I mean, not so close that it. But
How do you pick that? How do you pick that number? I mean, since you can pick the number,
yes.
how do you decide where it should be?
I actually can't answer you in detail on that. I know that all the people at JPL that calculate these orbital, the orbits they want to put them in and everything, it was something to do with when you put it in an Earth trailing orbit, you have some restrictions about. Basically, I don't know. I'm just, I'm tap dancing badly here. Okay, but yeah, I can find out for you though.
I mean, it seems that the angles you showed through that diagram very
Yeah.
nicely, but those,
Where is it? Yeah, there.
the way those angles converge to the focal point are going to be quite different if the distances are hugely different, right?
No, remember these are waves. These are I'm picking the waves. The waves don't care where I am. I can be here. I can be there. As long as I can see them. Just my field of view's changing, not the waves. The waves are doing whatever they want. Okay, now we move on to internal gravity waves. Well, yes, they're on the sun. They're really hard to see. Really, really hard to see. We made some measurements in 2002. We saw them, but we were hesitant. But there's been a measurement now by a spacecraft. It's called HMI. And what you do is they're looking at 2 different heights in the sun's atmosphere. And to cut to the chase here, this is what you would expect based on theory. This is what the phase difference is. It's basically a time that takes between the 2 layers. This is what we would expect on theory. This is what we can actually measure. This is unbelievable. This looks like it was fake, all right, but it's really real. Okay, these waves above the blue line here are just waves that travel straight out of the sun. They don't get caught at all, and we see that. But there was one aspect of this. So we see gravity waves. They're there for sure. Let me just go on. So what we did is we can do something. I don't know if you can see this. It might be a little bit hard. So we have this diagram of our oscillations that I showed you earlier. We can filter that, and we know that the gravity waves need to be in this region. So we can filter that out, go back and make a movie and see if we can see anything. And if you look, you can see all these waves going around in different directions. So we can see them, but it's really tricky to try and isolate individual ones to try and figure out, you know, what they're doing. But they're there, so we have some ideas on how to do this. Moreover, what was very exciting is when we measured the energy these things are carrying. Remember I said there's this enigma about the sun. You move away from 6,000, you go out towards the top of the atmosphere, and it goes to 1,000,000 again. Where's the energy coming from? Well, when you get to the top of the chromosphere, the amount of energy that you need that's being radiated by the sun is about whatever it is here, something 5×10 to the 3 watts per meter or something. Turns out that from what we can measure, the gravity waves are carrying about that amount. Now, I'm not saying that they're entirely responsible, but they're a player. They're certainly a player in this enigma. And the other thing we discovered is that they interact with these magnetic fields, which is going to be pertinent in a bit. You see here, these are pictures of magnetic field. This is part of the magnetic field. It's very low activity day, but everywhere you see this, you'll see that there was a reduction in the power of our gravity waves. So we know that they're interacting with the magnetic fields. Now, while I'm here, I just want to say one thing. Please look at this. In this phase difference diagram, there's a piece here that's white. There's no phase difference. We expect the atmosphere just to be moving evanescently, it's called, as one, okay? That's not what you see in reality. There's another phenomenon that we've struck on. What is it? All right, so a quick review here then. What's this phenomenon? So, properties of gravity waves. They got some strange properties. Okay, one is that they have their phase and their group velocities are opposite directions. What does that mean? Well, if I look at a group of waves, I have a packet of waves. In a packet of waves, I have waves that of different frequencies, and they travel different speeds. So the envelope may look the same, but the inside is moving around. So the phase velocity is how quickly this zero crossing point of the wave is, and the group velocity is that one. And you can see when we measure these that this is negative for the group travel time and positive for the phase travel time. So we say, yes, gravity waves. Thank you very much. But guess what? That was in here. So gravity waves are only expected here. Nothing's expected here. But we're measuring stuff with gravity wave-like properties there. We have no idea. I'll come clean. We have no idea what's going on. But the implication is huge because these gravity waves, this is, as we go this way, the wavelengths get longer. Okay, this means they can move a lot of mass and energy over a long distance, but also vertically. So So one of our goals in our coming experiments is to try and, you know, home in on this. So how are we going to do it? So we go back to our little movie we saw earlier, and another property of the gravity wave is that the angle at which it emits things depends on the frequency. So if we go to low, so as we go from low frequency, the waves are emitted in like it's called a St. Andrew's cross here. As we go up, the cross gets steeper and steeper until we get to a certain frequency, which is the Brunt-Vasila frequency. It doesn't matter what it's called, just stops happening. Now the interesting thing about gravity waves is, for example, the wave when it starts, there's nothing here as you saw earlier, and it travels that way. But the waves like you see in the ocean are traveling this way. Okay, it's kind of an odd beast. Here's the third property, which it's a little speculative, but I'm pretty excited about this one. Okay, gravity waves have a different property to light. With light, if a light comes in and reflects off something, we all learn at school that if you take the normal to it and the angle of incidence equals the angle of reflectance. No, gravity waves don't do that. What they do is they preserve propagation angle. Whatever they start out at, they keep it. You can't upset them. They want to go that way. All right? So that has a nice consequence. So you can see you've got an inclined surface here. It's just a schematic. All the waves come in it like this. They all collapse down. And it's called, here's my Alzheimer's. Anyway, it doesn't matter. What it does is it sets up. It can set up flows. Now remember, what reflects gravity? What interacts with gravity waves? That would be magnetic field. We've got magnetic field all in the sun. We know we have this magnetic canopy above like this. So it could be that gravity waves are not only moving stuff around, that they're setting up flows and contributing to the dynamics of the sun. Now remember, everything I say about the sun, if we can do it on the sun, we can probably do it on the planets. Okay. So for the gravity waves, we've got a couple of things lined up. 2 more seasons at South Pole, 2015, 2016, and 16, 17. Maybe even a third one. The other thing we're doing is we're building a CubeSat. I've told you about this. It's a 6U CubeSat, which is one unit's 10 by 10 by 10, so it's going to be about like this. That's like a cornflake box, a fat cornflake box. And we're going to do something nice. We're going to, instead of using a regular telescope, we're going to use a photon sieve. Basically, this uses interference as a way to focus light. This is just something with a bazillion holes in it. But the nice thing is, it doesn't have to be really a perfect surface. So it means it's like an umbrella that you can stick up. You're not too worried about the shape so much. It'll still work really well. So we're building some. We've designed for that now. We're starting to build stuff at JPL. As I said, and the actual instrument, we've managed to squeeze it down into something like this.
You say 10 centimeter cube.
Yeah, each one is 10 centimeter by 10, but we can stack 6 of them. So you have electronics in one, and you can take 2 with however you want. Okay, so let's see, in tonight's journey, we've been talking about looking into the interiors of the star in the sun and the planets. Okay, this is nothing new. Looking into the sun, 50 years we've been doing it. Well, that's new by a lot of science standards, but we've been doing it for 50 years. Okay, but we kind of hit a place where to make major advances, we need to see deep into the interior. So we're going to do that. We're lined up, space mission to Safari, go to the backside of the sun and do it. The last 10 years has seen an enormous amount of energy going into doing the same for other stars like the sun. There's hundreds now that we've looked at, and we can say all things about their convection and so on. It's really exciting. I didn't talk about that tonight. Most of the data that's useful for that is, again, coming from space missions. But just want to say, you know, it works for the sun. It works for other stars. Planets, we're in the infancy. This is great. This is the low-hanging fruit if we can make this work. And it's a big gains because, remember, we're going to figure out how the solar system was basically formed and evolved. That's it. So we're currently working on a ground-based instrument for proof of concept, and then we're lining up for this space mission, Uranus Explorer. Gravity waves, again, it's great. It's right at its infancy. Okay, and we've actually made some measurements. We've discovered a new set of waves, and we've been funded to go back to Pole. And we've got some funding, internal research money for doing the CubeSat. So even though we haven't made the big gains yet, everything's looking good. Okay, so for me, it's an exciting time. For you, it's probably exciting because I finished. So any questions?
The new solar telescope that's going to be built on Haleakala, will that be contributing to this effort?
No, the new solar, well, it could do, but the main purpose for the new telescope is to actually put the sun under a microscope, essentially, to look at its structures we've never seen before, much finer detail. Remember, my aperture, the size of something we can see depends on the size of your aperture on your telescope. So I'm 20 centimeters, that's 4 meters. Okay, but the thing is, when you look at 4 meters, you can only look at a little postage stamp of the sun. I get to look at the whole sun. But I think that, so one of the things that myself and a couple of my colleagues are looking at is how we can complement the new telescope that's going to be there, the DKIS telescope, with our experiments at Mies Observatory.
Okay, in one of your slides there, in the gravity wave phase diagram,
Yes.
you had the predicted and the observed.
Yes.
I've noticed there's some artifacts over on the left-hand side, down lower left-hand side there. You see, over the HMI, there's next, almost parallel to the red line.
Almost parallel to the red line.
Red line. I see
These?
some oscillations in there.
Yeah, this is it. These are the solar oscillations.
Very real stuff.
They're real stuff, yeah.
Delightful.
Yep.
From the virtual audience, question from Emmeline Starber. Question: what launch vehicle are you getting a ride on for the CubeSat?
That we haven't determined that yet. Apparently, might be able to figure it out because we can get four of them on there, I believe. Oh yeah. I'm being scolded. I'm not repeating the questions. What will be the launch vehicle that we'll launch our CubeSat on? Don't know, but we can probably work it out. Okay. All right. Thank you. So, if